Here we go. Let's grade. Number 10, there were horizontal tangents at 0 and 1. Did you factor? Oh, if you didn't factor, oh my goodness, you better write yourself a challenging note. All right. 14a, final answer is x squared minus 3 over x squared. Or, how could this be rewritten? Come on, we should know multiple ways. 1 minus 3 over x squared. Which would be easier to take the second derivative of? Pause. My voice is not doing well, so just hang in there with me. Try not to speak over me, please. Okay. People said 1 minus 3 over x squared, and I was saying, because this section has higher order derivatives, right? Some, second, third, fourth, whatever. What would have been easier to derive again? This quotient or the rewritten 1 minus 3 over x squared? I think the second one. But if you had to get it back into a fraction, some of you guys might argue with me. I'm not saying totally right, totally wrong. It's somewhat a preference, but it is nice to know this is 1 minus 3 over x squared also. Which could be rewritten as 1 minus 3 times x to the negative 2. Anyway, letter B, final answer. Oh, never mind. This is actually at the point of the problem. Anyway, whatever. Oh, because you could have rewritten it to begin with and not even done quotient rule. That's nice. That's something I would do. Number 16, final answer is 5x to the 4th plus 3x squared plus 2x. Remember, if you're acing all of these, show me that you're grading them with little check marks or a big old -0 at the end. Number 24 is 1. 24a, sorry. A is 1, B is negative 10.
This is A2.
Oh, can I not read? Sorry, over here it looks like a 1. Whoop. Yep, that's definitely a 2. I'll look at the screen. You guys are all like, oh. A is 2, B is negative 10, C is 10 ninths.
Oh, wait, it is 10 ninths?
It is 10 ninths. D is negative 12.
D is negative 12.
Oh, dear.
Yeah, I just didn't get B.
Uh-oh. A is 2, B is negative 10, C is 10 ninths, and D is negative 12. Number 28, 2x plus 5. 2x plus 5. Or y minus 3 equals 2 times x plus 1, or y equals 2 times x plus 1 plus 3. Depends on what form you got to. 34 was 2x plus 1, 2, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. What is the last unique derivative? I think you could stop at the third, right? But all the rest are going to be kind of pointless. Number 36. First derivative, negative 1 over x squared. Second derivative, 2 over x cubed. Third derivative, negative 6 over x to the 4th. Fourth derivative, 24 over x to the 5th. You guys remember they can use Roman numerals, right? But pause. The AP hasn't been using Roman numerals for a while. How would they have written this that confused some of you? They wouldn't have written the 4th as a Roman numeral. What would they? They could have done like this, or they could have done like, remember? They're doing it like this now. Not always the Roman numeral, they can be doing it like that as well. Wait, what? You had to find a pattern. Or just find a lot of derivatives.
I think we all got that.
Well, you should use the AP, like something to the power of 125.
There are some of those in homework. That's the funny point. Or the funny part. You guys got to the AP and you were like, 27. Ah! I'm like, we have that.
Something to the power of 1,500.
I hear it, but I'm saying that there are problems. No, you're not able to solve. Okay. Hey guys, you have another one, number 38. The slope is 4 at plus or minus 1. They found two different equations of tangent lines. You had y equals 4x plus 2, or y equals 4x minus 2. The smallest slope is 1 and occurs at 0. Minimize. Ooh, that sounds like optimization, but I don't think it was that hard, because this is in the chapter where you're barely learning the basics equation. Yeah, it was just a quadratic, wasn't it? Wasn't it an upward facing quadratic that's been shifted up one? Didn't get shifted right or left, so the min is just going to be at 0, 1. So it's actually using pre-cal skills of transformations of functions. Hey! Transformations of functions. Look, it's what's pre-cal doing. Anyway, parabola up 1. There was a min at 1. When x equals 0. I should say, I apologize, a min of 1 at x equals 0. I used improper terminology. Are we done? Yeah, we are. Let's go check out the next homework and see how long it is. Woo! It's not that bad. Anybody want a picture of it before I change the screen? You can't go too low or else you're going to start seeing all the answers. 1, 7, 9, 13, 19, 17, 18, 19, 20. They're all odd? No, except for 28. What are you going to do hard? Couple more seconds. People are writing. It's okay. It's okay. I'll let you get it. So we have 2 sections again. We have 2 sections again. And if you guys saw me scrolling forward in notes, you might have realized that the first word of section 3.4 and somehow a combination of 3.5, I believe, is velocity. Woo-hoo-hoo-hoo. Good thing we have kids in physics. Velocity. I mean, from the CalcBC. You don't need physics for this. Algebra. Oh, wrong one. Here we go. Velocity and other rates. Oh, I didn't even ask about homework questions. I'm sorry. Is there anything that we wanted to look at?
Can you explain
38? Yeah. You guys get started on notes and let me open up 38 to see what's going on. It's that weird minimize slope one, right? You guys open up notes and get going. Get started. Velocity and other rates. Which means this might be an interesting homework. P.S. Remember, I don't mind the talking if we're productive. And if some of you never do anything in class, at least not physically speaking as far as writing, you should not be distracting others who do. Woo! Whoa! This book in the very first chapter of Introducing Derivatives is starting to do related rates.
Nice.
Nice. Huh. That's interesting. But then do you guys also see all the motion stuff right below? Mm.
I know.
Why is a balloon square? What are we talking about?
So, like, there's a joke where a balloon is square, and then the girl went, "How do you blow a square balloon? Blow square rats."
Oh dear. P.S. There are a few of you guys that did not get the FRQ done for unit number 1 practice on AP Classroom. Someone was absent and totally missed that we even were supposed to do it, so I did unlock it. It is technically late at this point, but it is unlocked to where you can go on and finish or do Those FRQs, I noticed there were quite a few of you that never submitted it on AP Classroom. So I'm letting you know again that it is unlocked. The Unit 1 FRQs are unlocked, so you should be able to access them okay now. You turn them in for late credits. Oh, lunch is next.
Yeah, school.
Last year was period 4.
There's already
Keep on thinking of period 4. Okay. Lainey had a question really quickly on number 38. It was a weird one, and some of you just probably should have asked it and didn't ask it. So number 38. When it says find the tangent, careful. What's the terminology? What is it actually asking for? The lines. The lines. The derivative is a part of it, but they're asking find the tangents. They want the tangent, and the tangent is a line. Does that make sense? So when it said find the tangents, it literally meant find the tangent lines. Hence why you saw those first two answers were literally equations of lines. But the problem is they didn't tell me where. Oh yeah, they did. At the points where the slope, we had to go figure out what the x's are to even find our tangent lines. Now, slopes are the derivatives, right? So in order to figure out what points they want the tangents at, we would go ahead and say, okay, so f of when is, the slope's 4, I subtract the 1, divide the 3, I get c squared is equal to 1. That's going to be at the x values plus or minus 1, which is why we did, or they did, tangent lines. And you guys could finish at this point as far as each of those, and then y minus f equals f prime of negative 1, x plus 1. And I have full confidence you guys could solve, but then the problem wasn't done, right? Then it says, what is the smallest slope of the curve? Well, we just found the general derivative equation of all the slopes, right? So at that point, we just need to go think of, okay, what is the minimum value of this function? And so in my mind, without even thinking about optimization and maximums and minimums, I'm like, wait, he's a parabola. He's a parabola that's been shifted up 1. I know his min. His min is right here. So the minimum slope, the minimum derivative is going to be a value of 1 at or when x equals 0. And that finishes off the question. What is the smallest slope? 1. Smallest slope value, the smallest derivative is a value of 1. And when does it happen? At 0. So this was very much, like the math wasn't hard, but is very much a test of you guys able to, or being able to handle the vocabulary. Okie dokes. Here we are. What's going on, guys, in the beginning? Cylindrical balloon, radius 1/4 h. Find how fast volume is increasing when r is equal to 2. Why are they able to give this to us now? Yeah, and dV/dt isn't the same thing as just a simple dy dx, technically, right? Because they're introducing at the very beginning, well, even before, I think they were introducing rates with like the limit definition of the derivative, which our book kind of did last year. Every time we do a derivative, we're doing a slope of the tangent, but it could also be seen as a rate of change of the dependent or the y value or the function value with respect to time. So this is just a dy dx, a dV/dt, such that, or when, r is equal to 2. And the only way I can possibly do this is before I even tackle that, I need to figure out, okay, what's an equation of velocity in terms of radius? That's a pre-cal question. What's the velocity equation of a balloon in terms of radius? Well, hold on. What shape is my balloon? Okay. What's the volume formula for a cylinder? Right? Is it going to be pi r squared times h because it's the area of the base, pi r squared times the height? So it's pi r squared. Oh, but I don't want an h because I want volume strictly in terms of radius, so I can strictly plug in a radius and not have to do implicit differentiation. Supposedly, we haven't even learned it yet. So instead of h, I'm going to put in 4r. Good. because I need to substitute out the h for an equivalent statement. And doesn't h equal 4r because r equals 1/4 h? Take the time, guys. Take the time. I'm pulling out h, so I'm plugging in 4r. Take the time. Blessings upon you. Now, could we do a product rule? Sure. Do we want to do a product rule? No. Why don't we just simplify and rewrite? That was a big thing from last year, right? Rewrite first if it makes it easier. So how could I rewrite my velocity in, volume in terms of r? There we go. So what's my dv dt? Wait a minute. Is it dv dt? Why is it dv dr? Does it say with respect to time or bring in seconds or minutes or hours in any way, shape, or form? No. Ah, so it was just a dv dr. Look at me being all ready for related rates when it wasn't. I mean, it is. It's volume with respect to radius, but we're not talking about they're separate. It's okay. Makes you feel better. Maybe. No, when I make mistakes. And you catch me. You're like, oh, I caught her. Is it going to be 12 pi r squared and 12 pi r squared will be 12 pi 2 squared? What are my units? But why am I going to do the awkward inches cubed per inch? Pretend you still see the one. Because I'm talking about how volume is changing with respect to radius. If I just change inches cubed to inches squared, I've lost all meaning. Inches squared. What about inches? I don't. The areas? No. As the radius increases 1 inch, the volume increases 12 pi 2 squared. Well, okay, sorry. 48 pi, right? As the radius increases 1 inch, the volume increases 48 pi. Oh, wow. Okay, well, that's kind of a big deal. Sure. Like the oil spill in the ocean from last year. If we were talking about the radius increasing, could they theoretically like set up an actual point where they are outside the, it's just assuming it's like a circular spill and it's growing as a circle. If that's roughly how the oil spill would spread, couldn't they plant themselves a little bit outside of the oil spill and then time how long it took for the radius to spread to them, right? And then, oh, we saw the oil just reached us. How long did that take? And couldn't they then think about what that distance was from where the spill was to where it was now, and then couldn't they calculate, okay, about how many cubic, well, I guess it depends on what they're measuring, whether they're measuring gallons or cubic meters or anyway. But then they could think of the entire thing, think of the time. You can use the radius changing to see how the overall is changing. So don't simplify this to inches squared. You lose the whole rate. Keep it inches cubed because that's the volume measurement with respect to how the radius is changing. Okay? I know it's awkward, just say okay.
Yes.
Don't simplify. All right, what's going on down here? We know the position can be S, it can be X. Physics people, did you see anything else? No? Then let me help you out. How about parametric? Oh, you guys don't do parametric in physics. How lame is that? That's okay. We do it in CalcBC. How about X of t and Y of t? Can't a position be defined parametrically by what is the X at a certain time and what is the Y at a certain time? Uh-oh. Motion's going to get exciting. Don't worry, not yet. But technically, yes. You could just talk about a position like, hey, how high is it? Or how far is it? Or you could say how high and how far. Ooh, that's exciting. But let's not go into all the parametric motion stuff yet. Technically, it's the very last thing we do all year. It's kind of sad and kind of lame and kind of boring. But, well, it's not boring. It's interesting when we get there. We just don't get there very soon. But what's going on if whatever quantity we have is greater than 0 or less than 0? If you have a position curve or a position graph, my physics people? Nope. I'm not saying the slope is positive or the slope is negative. I'm saying the position is positive or the position is negative. What am I referring to? Above or below to above a reference point, right? And the reference point would be the 0, would be the origin. So I could say to the right or above, or to the left or below. The origin, or, I mean, you can make 0 whatever you want. It can be the top of the cliff, it can be the bottom of the ground, it can be like wherever a plane is, the top of a building. You can make 0 be whatever you want. So if 0 was on top of a building, wouldn't it be negative to get to the ground and positive to get to the plane? But 0 could be the ground, so then positive is up to the top of the building, or negative is in a hole in the ground. You can redefine positions. 0 can be the starting line, or 0 can be where the person gets handed off the baton in the relay race. 0 could be different places, but we're just saying to the right or above, or to the left or below. This is just position, right? So the position curve is positive above or below. That's talking about the position relative to something else. Now velocity, okay. Velocity, that's going to be not dv dt, dx dt, because it's the rate of change of position, right? Another way of saying it is we could do x prime. Of course, we could do dy dt, y prime, or we could do ds dt and s prime. The instantaneous velocity, we have to take the derivative of the position. It can be seen as, right, the slopes of a position curve or a position graph. You guys tracking? Velocity can be the slopes of the position curve or the position graph. Now go ahead and fill in what you were telling me a second ago. What happens if velocity is positive or velocity is negative? Then the slope is positive of a position curve, and if the slope is positive, how's the position changing? Increasing, or going more positive, or moving to the right or up. Does that make sense? So position being positive says the current location or the locations are to the right or to the left of something. But velocity signs say not only is it, well actually, velocity signs don't tell me whether it's to the right or to the left or above or below. Velocity only tells me if it's moving to the right, which could be on the left. That gets confusing. Or if it's moving to the left. And right now, guys, I'm saying just right or up, just left or down, because we are only talking about position in one dimension. Either right, left, or up, down. Everything gets exciting when all of a sudden it can be moving right, left, and up, down. Well, how do we know? Maybe we'd have to know the velocity in the x position, velocity in the y position, x prime and y prime. That's interesting. And then let's go to polar mode. We're doing everything differently, and not x's, y's, but theta's, r's. And we have to reorient again. But once again, second semester stuff. What else do we have? Speed. Physics people, we know that's magnitude, right? Speed, that's magnitude, absolute value. How is speed increasing? How is speed decreasing? How do we know if it's speeding up or slowing down? We have to check the signs of velocity and acceleration and see if they're working together or against each other, right? Keep on thinking classes done. I haven't gotten used to BC being during 5th period yet. Okay. I know you guys memorized it forever hard on speed, but can we at least just somewhat admit that it can still be a confusing topic for some, depending on how the question is worded, right? Because you're not just looking at the derivative being positive or negative, you're looking at the derivative and the second derivative if you're given position. But of a graph, it should kind of make sense. I know in physics you guys have been talking about position curves or velocity curves, or did you do acceleration curves? Not really. But knowing all that we know about calculus, guys, it hasn't even been covered in this textbook yet, but with increasing and decreasing and concave up and concave down. Let's think about it. If the first derivative and the second derivative are both positive or both negative, what would the graph look like of position? Okay, so the slope is positive and the concavity is positive, or the slope is negative and the concavity is negative. See what I'm saying? It's either concave up and increasing, or it meaning position, or it's concave down and decreasing. Think about both of these. Either the tangent line is positive, the slope of the tangent line is positive, and the concave is up, or the slope of the tangent line is negative and concave down. What's going on? If the rates are the slopes, what's going on to the slopes? They're getting steeper. If the slopes are getting steeper, the magnitude is getting higher, right? And then what's going on here? The slopes are getting steeper. If the slopes are getting steeper, the magnitude is getting higher. Yes, I know it's negative, but if it's negative, it meaning velocity meaning moving left and concave down, yes, the negatives are working together. Steeper, steeper, steeper means faster. I couldn't show you necessarily that last year when we first talked about it, because we hadn't talked about increasing, decreasing, concave up, concave down. But now I can. But what's going on in this case? If the signs are opposite. Well, if velocity is positive, acceleration must be negative. So a positive tangent line, but a negative concavity. Wouldn't that be the other type of concave? Well, here, let's do it so that they're paired up. The other concave down will be going this way. So if the acceleration is negative, concave down, and the velocity is positive, do you see how my slopes are decreasing? Or the magnitude of my slopes, my speed is decreasing. It's getting closer and closer and closer to zero. It's slowing down. Or the other portion of this, it would be this one, right? Concave up, and yet the slopes are negative. The signs are opposite. Isn't it also slowing down? Interesting. It's very logical, and yet it's so hard for us to remember. We have to check both signs and then compare and see where they're the same or where they're opposite. Acceleration. Velocity is increasing, velocity is decreasing, because remember, what is acceleration with respect to velocity? Key is the rate of change of velocity, how velocities are changing, which is the same thing as, since you guys did higher order derivatives, you reviewed that notation already, right? Second derivative of position, first derivative of velocity. Acceleration, velocity is acceleration is positive, velocity is increasing, acceleration is negative, velocity is decreasing, but be careful. A positive number increasing is gaining magnitude, but a negative number, there he is. A negative number increasing, oh, that's awkward. A negative number increasing, what does increasing actually mean? Getting stronger? What does increasing mean in math? Math, numbers, increasing. What are the negative numbers doing if they're increasing? They're headed in what direction? Towards positive numbers. And if negative numbers are headed towards positive numbers, aren't their magnitudes decreasing? All things to keep in mind when we're dealing with signs, positives and negatives, and rates of change. Increasing means the numeric values are going more positive, right? When dealing with velocity where the signs are important. If it's increasing, if increasing as a word is being used with magnitudes, oh great, the magnitudes are increasing. Here though, the numeric values are increasing. Remember, this is why that is confusing. This one you could say the numeric values are going towards positives. This one you can say magnitudes are growing. So speed increasing, magnitudes are growing, velocity increasing. Well, the numeric values are going more positive. So positives, more positives, great. Negatives, more. See, it came in. There you go. Negatives, more positive. Oh. Jerk, who's that guy? Don't start saying names. Think about the pattern. Think about the pattern. Jerk is the derivative of acceleration with respect to t, which is the same thing as the second derivative of velocity with respect to time, which is the same thing as the third derivative of position. That's one that's been on sweatshirts before. The sad part is AP test doesn't include jerk, which is kind of sad. Exactly. That's a good one. It's a funny one. We haven't used it in a few years. We said don't be a position triple prime. That's the next thing. Oh, don't be a jerk. Or you could say CalcBC, where the only jerks are. No. We don't do it. That doesn't. Anyway, but why? If someone's just learning a stick shift, what's the car gonna do? A lot. Sure. Right? That's what happened when I first started stick shift. I had to learn on stick shift actually messed
I
up
drive a self-driving.
But coming back. Let's not even talk about that. Okay. Or if your transmission's going out, you'll be good too. Anyway. Because acceleration changing and how acceleration changes, that's the jerk. This is how your speed is changing, speeding up, slowing down, and then if your acceleration is changing, then you start to feel the other. Anyway, sadly though, once again, not on the AP and not in your homework. Hey, P.S. In sections 3, 4, and 3, 5, a couple more things to finish off the chapter. Do we still remember all of our trig derivatives?
Yes, basic.
Give me the basic ones. Derivative of. Derivative of cosine is. Aw, integrals didn't mess you guys up horribly. Careful, knowing which one's positive, which one's negative, right?
Are the tangent ones constant?
Huh?
Tangent, secant,
Mm-hmm. Oh, I had too many lines. Too much time. Derivative of tangent. Derivative of cotangent. Derivative of secant. Okay, why am I putting this? What if we forget them? What am I referring to? Yeah. For all of these four, right? As long as you know the derivative of sine, the derivative of cosine, and the quotient rule, couldn't we always do derivative of tangent as derivative of sine over cosine? I'm not going to do it this year. I did last year. Right? Or to do the derivative of secant, couldn't we do ddx of 1 over cosine? To be the same thing as ddx of, we can cheat and use the chain rule because we can do that, right? It's technically not until chapter 4. That was how it was last year too. You guys had to test just some basic derivatives before the chain rule. Not quite sure you guys would say it was easy. Now you should. Then I think it was still a hard one. So do you have resources that you guys sometimes forget?
Yes.
Did I have some of you messing up on forever quizzes all year long on some of these? Yes! And then you do integrals and then it's like, everything's all mixed up. Speaking of which, though, we will learn how to integrate secant this year. That'd be fun. We were never able to last year. We would have had to have memorized the integral of secant. Who's that? Because he's not one of the derivative rules. The integrals go backwards. If it's not a secant squared or a secant tangent or a cosecant squared or a cosecant cotangent, remember signs. We got that. We would have been in trouble. We'll learn something this year. Integration by parts. Lucky 7. Tic-tac-toe from Stand and Deliver, but that's not until later. All right, homework number 9, section 3435, due tomorrow. You guys already wrote it down. We have approximately 10 minutes left of class. Let me see what I can show you. What? What do you have from the beginning? Anything exciting? 1, 7, 9. I'll show you number 1. Because he has 4 parts. Here you go. Ready, set, start. Oh, this is so annoying. You make us write the words. Pause. If this was an FRQ, I would want you to read it quickly and summarize it quickly to be able to know the important information. So isn't V just saying find V of S? For a Q? A. Q, colon, find V of S. Perfect. V. Find V prime of S. C. Find average rate. V of 5 minus V of 1 all over 5 minus 1. Oh my goodness, I'm doing it for you. Go. Go, go, go. Do you guys like the whole homework problems in Google Classroom? All right, I'm not going to do it all year long, but these ones, since we're done early, I'll go ahead and go get you nice copies. Huh, I heard my name. I don't know.
Wait, so if I wanted to leave school,
Oh. Oh, I was thinking the picture.
So what if I had a doctor at lunch and my mom finding things like that?
What are we on? Homework number 9?
I'll have a lot of doctor's appointments.
What? Just say no. No doctor's appointments.
I like that. The picture. That's how one. As a top.
I was getting so confused. I'm like, what?
I wanted to. Are we going for one that we will sit or like a BC?
P.S. You know more calculus than CalcAB does. You guys can totally get your sweatshirt if you can work together done quick. And then make them jealous.
Yeah. That's hilarious.
Work together. Although I think last year, juniors pretty much just, those with strong opinions have them, and then those without are sure, whatever. I think seniors last year were the ones, the other class that was no, we don't want that. Because no one had a strong opinion against it, whereas all the other ones someone did.
I want the same colors as
Was it the dark gray, the dark charcoal, whatever?
Yeah.
Let's get some yellow hoodies.
No.
Yeah. That's what we're saying.
No.
We got pink ones.
Because the French? Why are we getting pink because the French? Because BC is cool, the French kids are cool.
Blue.
Talk them into it, Abby. It's not me. Talk them into it. A mint blue? A mint green? It'd be good for St. Patrick's Day.
No, we should do blue.
Like dark blue? We had a dark navy blue for our BC one a couple years ago. It was a crew neck.
Is there a difference?
That's white. That is white. All of these
See of which one. Right, colors.
I don't think it matters.
You guys want me to go to number 7? Are you done? No.
Yeah.
Kyle didn't